Assalamualaikum warahmatullahi wabarakatuh.
Welcome back to the deep dive. So look around you. 70% of this planet is, well, salt water, the ocean.
Right.
Yet global water scarcity is, it's one of the biggest crises we face. It's this huge paradox.
It really is.
And the technology bridging that gap, that's our focus today. Desalination. Turning the sea into drinking water.
Exactly. And our mission today really is to get under the hood of that massive engineering effort. We'll look at the dominant technologies running things now.
Like reverse osmosis, the thermal plants.
Precisely.
Yep.
And the big problems they cause, we're talking serious energy use and that toxic brine issue.
Okay.
But then we'll look forward to the really revolutionary stuff coming up.
Yeah.
Graphene, AI, maybe even zero liquid discharge.
And importantly, we'll bring this back to you, the listener, especially if you're thinking about high-capacity off-grid water, what actually works reliably.
Yeah, because modern desalination, it's actually way more complicated than just filtering salt out.
That's what I found fascinating.
It's not just the membranes or the heating. Those are key, sure.
Yep.
But the really critical part, the bit that makes the water actually usable, that's the post-treatment.
Post-treatment, so after the salt's out.
Right. We can make incredibly pure water, purer than rainwater. But if you don't carefully remineralize it, adjust the pH, preserve it properly,
And then what happens?
it's useless. Or worse, it's actively harmful. It'll corrode pipes, plumbing, everything, and it's not even good for you. So that post-treatment, absolutely essential.
Okay, let's start with the current giant in the room. Reverse osmosis, RO.
Yeah.
The numbers are pretty stark, right? It's like 70% of global capacity now?
Easily.
Oh.
Yeah, around 70% by 2024. It's just scaled incredibly well, and relatively speaking, it's energy efficient.
So how does it actually work in simple terms?
Well, the physics are kind of straightforward. You basically need immense pressure.
How much pressure are we talking?
Oh, huge amounts. Typically 50 to 70 bar for seawater, so 50 to 70 times normal atmospheric pressure. And you use that pressure to force the water molecules through these special semi-permeable membranes. The salt ions, minerals, they get left behind.
But you mentioned efficiency. That amount of pressure sounds like it takes a lot of energy.
It does. But the big leap forward in modern RO wasn't just better membranes. It was being clever with the energy you've already used. Energy recovery devices.
Go ahead, tell me about those.
They are critical. Things like pressure exchangers. They sit on the waste stream, the brine.
Stuff left behind?
Exactly. And they capture the hydraulic energy, the pressure, before it's discharged. Some can recover up to like 98% of that energy.
98%, that's huge.
It is. And that single piece of tech can cut the overall energy cost by 30, maybe even 50%. Without that, honestly, RO probably wouldn't be as dominant economically.
So RO is efficient, relatively speaking, but it's not the only method. Particularly, you mentioned the Middle East, where maybe they have existing power plants. That's where thermal comes in.
Correct. Yeah, thermal methods really shine when you've got a source of heat handy, often waste heat. We're talking multi-effect distillation, MED, or multi-stage flash distillation, MSF.
Sounds like boiling water, basically.
In a very sophisticated multi-stage way, yes. Evaporation and condensation over and over, very efficiently. And often, they're paired directly with power plants, using heat that would otherwise just, go up the chimney.
Makes sense. Any other thermal types?
There's also mechanical vapor compression, MVC. That one's a bit different. It uses mechanical compression to heat the steam directly. Super energy efficient in terms of heat, often used for smaller standalone industrial jobs.
Okay, so whether it's pressure with RO or heat with thermal, we've done the hard work. We've got this pure H2O. But here's the twist you mentioned earlier. This perfect purity is actually bad.
From a practical chemical standpoint, yes.
Yeah.
It's a massive flaw, ironically. This desalinated water is too pure.
How can it be too pure?
It lacks essential minerals, calcium, magnesium, stuff naturally in water.
Yeah.
And its pH is very low.
Mm-hmm.
That makes it aggressive, corrosive.
Corrosive enough to damage pipes.
Oh, absolutely. It'll eat right through metal pipes, concrete distribution systems, expensive infrastructure. Plus, water without those minerals isn't ideal for long-term health.
Right. So, okay, remineralization. It's not just nice to have, it's mandatory for the pipes and for people. How do they actually fix this hyper-pure water?
So remineralization is all about restoring that chemical balance. Getting the pH stable, usually aiming for maybe 7.5 to 8.5, somewhere in that neutral to slightly alkaline range, and putting those essential minerals back.
And the most common way sounds surprisingly simple. Limestone, like actual rocks.
Pretty much. Limestone dissolution. It sounds low-tech next to RO membranes, right? But it's incredibly effective, stable, and cheap. You just pass the permeate water through beds of crushed limestone, calcium carbonate. Often, they'll inject a bit of CO2 gas as well. That helps the limestone dissolve more effectively and adds carbonate alkalinity, which helps buffer the pH, makes it stable. It sort of mimics how water picks up minerals naturally.
Is there a faster way? Maybe more high-tech?
Well, there's lime dosing. Using hydrated lime, calcium hydroxide, it is faster and easier to automate for large plants.
But there's a catch.
Yeah, the downside is it can make the water cloudy, increase turbidity, and it produces quite a bit more sludge, this sort of chalky waste product that then needs to be dealt with. So for stability and less waste, that limestone contactor method, often with CO2, is really the industry standard.
Okay, so we've got the main methods and this crucial finishing step, the remineralization. But let's talk about the big persistent problems, the headaches that keep desalination from being, the perfect global solution. What are the main roadblocks?
Number one, without a doubt, is the energy demand. It's just massive.
Even with those recovery devices we talked about.
Even with them, modern RO still eats up something like 3.5 to 5.0 kilowatt hours for every cubic meter of water, every 1,000 liters.
And translate that into cost.
Energy can be up to 60%, 60, of the total operating cost of a plant. Globally, get this, the daily energy consumption is over 200 million kilowatt hours every day.
Wow, that's a staggering amount of power. Even if it's renewable power, that's a huge demand on the grid or the generating source.
Exactly. It strains infrastructure. So that's challenge one, the energy beast. Challenge two is equally, maybe even more concerning environmentally, the brine.
Right, the salty wastewater left over.
Hypersaline brine. And the ratio is just terrible. For every liter of fresh water you make, you generate, on average, about 1.5 liters of this concentrated brine waste.
Wait, more waste than fresh water produced?
On average, yes. And globally, the sheer volume is mind-boggling. Plants are discharging around 142 million cubic meters of this stuff every single day. And that number's up 50% from previous estimates just a few years ago.
And it's not just extra salty water, is it? There's other stuff in there.
That's the critical point. It's loaded with chemicals from the process. Anti-scalants, biocides to kill microbes, leftover chlorine, sometimes heavy metals leached from equipment. It's a toxic cocktail.
So when it gets dumped back in the ocean, it doesn't just mix in?
No, because it's much denser than seawater. It sinks, it flows along the seabed, creating these layers of super salty, low oxygen water, like an underwater dead zone.
Killing life on the seafloor.
Precisely. It wipes out the benthic organisms, the worms, the crabs, sponges, the base of the local marine food web. So you're solving a water problem on land by creating a potentially serious pollution problem just offshore.
Which really underscores why people are pushing for this idea of zero liquid discharge, ZLD. You can't just keep dumping it.
You really can't sustainably. Which leads nicely into the third big challenge, which is more internal to the plant. The membranes themselves, particularly in RO.
They're the heart of the system, but they're fragile.
They're high maintenance. The big enemies are fouling and scaling.
Okay, what's the difference?
Fouling is basically gunk building up biofilms, organic matter, tiny particles clogging the membrane surface, reduces flow, needs cleaning. Scaling is when the dissolved salts themselves start to precipitate out, like limescale in a kettle, but much worse. Hard mineral deposits.
And cleaning them isn't easy.
No, it requires harsh chemicals, it takes the system offline, it costs money, and uses more energy. Plus, the cleaning agents, especially chlorine, which is often used, degrade the membrane material itself over time. They just don't last forever.
All right, we've laid out the big problems. Energy, brine, membranes. Now for the exciting part, the future. What are the breakthroughs on the horizon that could actually fix these issues? Let's start with the one that gets a lot of hype. Graphene.
Graphene. Specifically graphene oxide membranes, They are probably the most talked about potential game changer for membranes. Lab results are incredibly promising.
Better filtration.
Yes, potentially higher salt rejection, maybe up to 97% compared to the 90-95% typical for current RO. But the really exciting part isn't just slightly cleaner water.
It's the energy, right?
It's the energy. The unique structure of graphene might allow water molecules to pass through more easily, perhaps with less pressure needed than conventional RO. Think filtration happening more naturally.
Less pressure equals less energy.
Exactly. Plus, graphene itself is incredibly strong and might have inherent antimicrobial properties that could directly fight that fouling problem we just discussed.
So what's the holdup? Why aren't all plants using graphene now?
Manufacturing. Making these intricate membranes consistently, reliably, and crucially at the massive scale needed for municipal water supplies. That's the big hurdle they're still working on. Cost-effective mass production.
Okay, so graphene is promising, but maybe a bit further out. What else is gaining traction? You mentioned forward osmosis, FO.
Right, FO is different. It's already being used commercially in some niches. Instead of using high pressure against the osmotic gradient like RO, it uses a special draw solution on the other side of the membrane. This solution has an even higher concentration than seawater, so it naturally pulls the fresh water across the membrane.
No high-pressure pumps needed then.
Essentially no, or much lower pressure. The big advantage is it seems to be naturally much less prone to fouling. There was one plant documented that ran for 19 months straight with no chemical cleaning needed.
19 months. That's incredible compared to standard RO cleaning schedules.
It really is. So it's great for tricky water sources like industrial wastewater or applications where you need gentle concentration, maybe in the food industry. The challenge is regenerating that draw solution efficiently.
Then there's a really different approach. Capacitive deionization, or CDI. This sounds like a totally different way of thinking.
It is a paradigm shift. Instead of pushing water away from salt, CDI uses electrodes to pull the salt ions out of the water, electrochemically, like tiny ionic magnets.
So you're removing the salt itself, not extracting the water.
Exactly. And the really clever part is the energy use potentially scales with the amount of salt you remove, not the total volume of water you process.
Yeah.
So for brackish water, which is less salty than seawater, it could be much more efficient.
And no high-pressure pumps.
Nope. And theoretically, you can even recover some energy during the regeneration step when the electrodes release the captured salt. It's still developing, but it's a fundamentally different, potentially much more efficient approach for certain applications.
Beyond new materials and processes, technology is also just making existing plants smarter, right? AI is playing a role.
Oh, absolutely. The digital revolution is hitting desalination hard. AI and machine learning are being used for predictive maintenance, figuring out when a membrane needs cleaning before it fails badly, and for real-time optimization.
Like a digital twin.
Exactly like a digital twin.
Yeah.
Simulating the plant's operation second by second. Big plants, like Saudi Arabia's Ras Al Khair facility, are monitoring tens of thousands of sensors, maybe 27,000 or more.
27,000 sensors.
Yeah, feeding data constantly into AI systems that tweak pressures, flow rates, chemical dosing, everything to squeeze out efficiency gains. We're seeing energy reductions of 15, even 20% just from smarter operations.
So tying it all together, graphene, FO, CDI, AI, they're all tackling those core issues of energy, membrane life, and maybe indirectly brine.
They are. And the overarching goal, the direction the whole industry has to move in, is that zero liquid discharge, ZLD. Finding ways to treat that brine, extract valuable minerals or salts, maybe even produce more fresh water from it instead of just dumping it.
And renewables, obviously.
Absolutely critical, integrating solar, wind. Solar thermal is interesting too. There are systems now using molten salt or other materials as thermal batteries storing the sun's heat during the day to run the desalination process 24/7.
Okay, let's shift gears and make this really practical for you, our listener. Imagine you're setting up, say, a large off-grid homestead. Maybe 10, 14 people, you've got animals, a decent-sized garden. Your water needs are significant, maybe 2,000, 5,000 liters a day, maybe more. Those little backpacker filters aren't going to cut it. What's the realistic, reliable option?
Yeah, for that kind of scale, you need something substantial. The sources really point towards a hybrid approach as being the most resilient and cost-effective over the long run.
Hybrid meaning?
Combining two main things: a good-sized, solar-powered reverse osmosis system, something rated for maybe 2,000 to 4,000 liters per day, matched with significant rainwater harvesting and storage.
Ah, so you're not relying solely on the RO, which depends on sunshine.
Exactly. The rainwater collection acts as your buffer. When it rains, you use that primarily, maybe storing weeks' worth if you can. That takes the pressure off the RO system, saves energy, reduces wear and tear.
And when it's dry and sunny, the solar RO kicks in.
Right. But having adequate storage is key. You need enough tank capacity to ride out cloudy periods or times when the RO system might need maintenance. We're talking probably 3, maybe even 7 days worth of your total water usage stored. That gives you real security.
Okay, that makes sense for reliability, yeah. But solar R systems, especially high-capacity ones, aren't cheap up front. What if the budget is just extremely tight? Or you just need a bare-bones emergency backup?
Right, for the absolute lowest initial cost, or just for a sort of last resort backup for drinking water, the recommendation is usually DIY solar still, or several of them.
Solar distillation, basically using the sun to evaporate water and collect the condensation.
Exactly, like a mini greenhouse effect in a box. The beauty is its simplicity. Costs can be incredibly low to build, maybe $50 to $500 depending on materials and size. Maintenance is practically zero, just keeping it clean, and it uses no electricity at all, completely passive.
Sounds great, but there must be a catch, the output.
Yeah, that's the massive limitation. Output is very low. You might get maybe 2 to 10 liters per still per day, depending on sunshine and design.
2 to 10 liters. That's barely enough drinking water for one person, let alone a whole homestead with gardens and animals.
Precisely. It's absolutely not a solution for the kind of volumes we were talking about earlier. It's really only suitable for providing emergency drinking water for 1 or 2 people, or maybe supplementing other sources slightly. It's life support, not a primary supply for high demand.
So for that bigger off-grid scenario, managing the demand side is just as important as the supply side.
Oh, totally. The cheapest, most sustainable liter of water is the one you don't have to produce in the first place. So things like efficient drip irrigation for the garden instead of sprinklers.
Mulching heavily to keep moisture in the soil.
Right. And looking seriously at gray water recycling, using water from showers and sinks for irrigation, properly treated, of course. All those things dramatically cut down the total amount of purified water you actually need the RO system to produce.
So wrapping this up, we've seen an incredible engineering involved, not just in getting salt out, but in making that water stable and safe afterwards, that crucial post-treatment.
Yeah, that remineralization step is huge.
And then looking ahead, these amazing technologies, graphene, CDI, AI, are tackling the big hurdles to make desalination more sustainable, more affordable.
They really offer hope for addressing the energy and brine problems. And that brine issue, environmental rules and just, well, common sense, are pushing the industry hard towards zero liquid discharge, ZLD.
Right. It's not sustainable to just keep making fresh water by creating these toxic brine plumes offshore.
No, you have to close the loop, turn that waste into something useful.
Which brings us to a final thought for you to chew on. Maybe the real test, the ultimate measure of success for the future of water security. It isn't just how good we get at pulling fresh water out of the ocean. It's how clever we become at turning that brine, that toxic byproduct, back into a valuable resource. What could we recover from it? Lithium, magnesium, other valuable elements. What will the brine streams of the future actually yield? Something to think about.